So now we're going to go into the background of what is the CFD module. What is this tool? What can it do for us? The Computational Fluid Dynamics, or CFD module, enables you as a designer to easily design, build, simulate, and optimize the piping systems that are really the foundation of our GHX systems, ground heat exchanger systems. Why do you want to optimize a piping system? Well, you want to ensure that the system can be purged, first and foremost, and then you want to ensure that the system provides effective heat transfer with minimum circulation pump costs. Those are the two primary goals here. So what can the CFD module do to help us with this? Well, the CFD module can help you model piping systems that consist of a wide possible range of connected components, including manifolds, supply return runouts, supply return headers, single and double U-bends, the fittings that connect the systems together, and circulation pumps. So can't you do this by hand? Well, people do, but you can't really do it with accuracy. Turns out modeling reverse return systems is unbelievably complicated and really impossible to do with any accuracy by hand or even with a spreadsheet. Plus, it takes hours to make modifications and redo the calculations. With the CFD module, however, it only takes a few seconds. It's really quick. So how does the CFD module do this to help you with it? It uses a drag and drop design methodology, and then the CFD module can automatically design flow balanced direct and reverse return systems while providing you as a designer with the flexibility that you need for standard and non-standard systems. So what are the results that you get out of this module? Well, you get your flow rates, your fluid velocities, your Reynolds numbers, your pressure drops, your fluid volumes, and the like for every single component in this dynamic geothermal piping system. Now we're going to briefly look at standard nomenclature for geothermal piping systems, specifically how it relates to this use of this module. So this is one piece of terminology that may be new to a lot of you. We call it the GHX module. And this is defined as a completed assembly of GHX components, including the GHX supply return runout, the GHX header, and the GHX circuits. So we can see our supply return runouts here. We see our headers here and our circuits here. And this, everything that's in the red dotted line here, is what we call a GHX module. This is kind of the fundamental unit that we build inside of the CFD module, the GHX module. Lots of modules here. And a GHX field is basically an assembly of GHX modules connected to your building or group of buildings via manifolds or vaults or whatnot. Generally, when you're doing a design for purging, we purge one GHX module at a time. So you'll purge this module, you'll purge this module, and you'll purge this module. You typically will not purge the whole GHX field or system in one fell swoop. Since we do generally purge one module at a time, we're going to be designing GHX modules one module at a time inside of GLD. So that's the nomenclature. Really, the only new thing here is GHX module, which is, again, your supply return runout, your headers, and your circuits, heat exchanger circuits or boreholes. Now we're going to take a very brief review of reverse return systems. A lot of you probably already know this. Some of you may be new to geothermal, maybe not, may not know this, so we're just going to cover it briefly. So basically, this is a basic standard reverse return system where the fluid flow path is as follows. It comes down here from supply runout, and then it branches, some branches into this first borehole, and then reverse returns. This is why it's called reverse return, because it sort of reverses before it returns. The fluid that doesn't go down that first borehole continues down here, and then some will go into the second borehole before reverse returning. The remainder continues down here before heading through the last heat exchange borehole and before coming back. That's the basics of a reverse return system. And here's what it looks like inside the CFD module. So we have this schematic of a reverse return system with 8 boreholes. And inside the CFD module where we build this piping system, it would look like this. Let's spend a moment here looking at how these two images correlate with each other. So we have a supply runout and a return runout. You see they're non-equal lengths. Inside the CFD module, here we have our supply runout and our return runout, indicated by this basically element here. While these look like they're the same length, we have control to specify what the lengths are of the supply and return. We have our first borehole here, our first circuit here. We have our header section 1 here. We have our header section 1 here. You'll notice that the header section is crossed over like an X. This is to indicate a reverse return system. If we're designing a direct return system, it looks a little bit different. We have our second circuit or second borehole. We can go all the way down to our last borehole here, number 8 here. So this turns into this in the CFD module. And the flow path that we model inside the CFD module is exactly the same as I demonstrated before, and it's very complicated, as you can see. There's absolutely no necessity to think about this, or know this, or understand this, or worry about this when you're using the tool, because it does it for you. So we're getting close to the good stuff. Now we're going to look at purging design for reverse return systems. This is kind of where we get into the heart of this presentation today. So again, as a refresher, a piping system or a GHX module must be purgeable with an available purge pump. It does us no good if we design a system that we need to have a nuclear-powered purge pump to purge. We want to design systems that we can purge readily and easily. Second, we want a minimum 2 foot per second fluid velocity throughout the entire system to purge air effectively. Now, a lot of people will argue with this and say they want higher velocities. I say use whatever velocity that's worked for you in the past, although, you know, if there's other debris in these loop fields, higher velocities will be warranted. Like, I've seen pictures of people dropping cell phones into these, pipes, and in some cases, it took 6 feet per second or more fluid velocity to get that stuff out of there. With the GLD CFD module, you can specify what your target velocity is, and then the program designs the piping system based off of that. Again, another thing that's important to know is when you're purging your system, you're going to be using water. You're not going to use a freeze-protected solution. You're just going to be using water. All the calculations that we do inside GLD for purging are done with water. So basically, this is 2 pictures of a standard reverse return system. At the top, we see sort of the bones, the basic layout. I know it's going to look a little small on some of your screens, so I'll read it to you. Here we have a 2-inch supply pipe, 200 feet long. We have our first borehole, which is a 1-inch pipe, 300 feet deep. We have our first header section, which is 2-inch pipe, 20 feet long. All of our other headers are 2-inch, 20 feet long, and all of our other circuits are 1-inch, 300 feet deep. And then our return here is 2-inch, 340 feet long. Basically, this is the bones. It hasn't been purge optimized. What we want to achieve is something that looks like this, 2 feet per second throughout every component of the design. That's what our target is here. Now, if we take a purge pump that gives us about 45 GPM at 6 or 7 feet ahead, we can achieve 2 feet per second velocities in all the circuits. Look down here. Every circuit is 2 feet per second or higher. And some of the header sections as well are 2 feet per second or higher, as you can see. However, some of the header sections here and here on this reverse return module are not achieving the target velocity of 2 feet per second. In other words, the GHX circuits are being purged, but the headering is not. So to achieve our 2 feet per second velocity, we really need, in this case, to increase our purge pump capacity or size. Let's do that. So now if we really bump things up to about 146 GPM and 345 feet ahead, which is, pretty darn high, you'll see we're going to achieve 2 feet per second or higher throughout the whole system. You'll see throughout our header section here, here's 2 feet per second, 2 feet per second, and so we're good there. But on the other hand, now we're at 6 feet per second here and 15 feet per second here, which are really, really high velocities. And then we can see that our head loss, this purge pump is kind of ridiculous. This clearly is an unreasonable purging process, and this is the justification for using the use of a reducing header system. This is why we do reducing headers, for purging. Reducing header systems enable purging velocities throughout your GHX module while maintaining reasonable flow rates and pressure drops during normal system operation. That's the whole purpose of these reducing headers. So basically, to repeat that, reducing header systems enable purging velocities throughout a system while maintaining reasonable flow rates and pressure drops. So for example, with a reducing header system here, you can see how the pipes are getting smaller in diameter as you go by the thickness here. We're able to achieve 2 feet per second or higher velocities throughout the entire system while having a reasonable purge pump. You can see the purge pump here. This is reasonable. That's why we have reducing headers for that purpose, for this purpose. So a lot of times as designers, we may design a system, we engineer a reducing header system, and then we put it into the and then we basically print our reports, and we have the construction crews build these things. And we need to be careful to make sure that they are constructing it to spec. If someone in the field basically may not understand the purpose for the reducing headers, and they may say, oh, I can't find that 1 1/4 inch pipe, I'm just going to put a 1 inch pipe here, no one's going to know it's going to be buried. What kind of effect can that have? Let's take a look. Here we have our supply return run out here in our header sections 1 through 7 from the previous design. And this is basically the way the pipe was designed. It started as a 2 inch in the headers, then it dropped to 1 1/2, 1 1/4, and 1. On the return side, it started 2 inch, and then it basically just sort of mimicked and reversed the supply side. And these are the velocities we saw a moment ago. Now, what if we change one thing? What's going to happen? For example, if I take this 1 1/2 inch pipe here, I turn it into a 2 inch pipe, or I take this 1 1/2 and change this into a 2, suddenly my purge pump has to go up a little bit. Originally, I was at about a 47 GPM, and this is my feet ahead. But now when I made that one change, it jumps up a little bit. It's not a huge difference, but it is a difference. If we change another thing, though, basically all hell breaks loose. If someone in the field doesn't understand the reason for the design, and they say, oh, I can't find that 1 1/4 inch pipe, I can't find this 1 1/2 inch pipe here. What if I put a 2 inch pipe here? And they do the same here. Suddenly, my purge pump to achieve 2 feet per second is basically essentially double. This is why it's really important to make sure that what's being installed is spec'd for the headering design. So basically, all the preliminary stuff is done now. I've kind of introduced you to the CFD module, why we do reducing headering, et cetera, et cetera. Now we're actually going to use the CFD module to design these systems. You're going to see how easy it can be to basically save yourself a lot of time in the design process. Just a couple basic things to note for people that haven't used this module before. There are 2 key components in this module, the GHX circuit, which you can see on the left, and the pipe pair on the right. And you can think of them kind of like Legos. The GHX circuit on the left has a large number of components that we can define and control if we want to. We can do supply side fittings, reverse side fittings, supply side pipe, reverse side pipe, the U-bend at the bottom. We can control the type of fittings, the fitting pipe size, the equivalent length of the fitting, names, volumes, inner diameters, outer diameters. There's tons of things we can control if we want to. Typically, the automated functions do most of this for us, though. For the pipe pair, like the headers or the supply return runouts, the same principle. There's a lot of things that we can define and control. And then we just snap them together basically like Legos to form a system. Here, if we snap these together on the screen, it'd be a very, very simple direct return system with 2 boreholes on it. Now we're going to take a look at the CFD module itself. We're going to spend a couple minutes looking at the manual design techniques which are available. Then we're going to look at the automatic design methods and how they pertain to headering design. And then we're going to open this up to questions. So here's GLD 2012. We're going to open up the fluid dynamics or piping module here. I'm going to spend about 1 minute going over a very quick tour of what this thing is. First thing to know is you can change the size of this. Some piping systems are very large, and so we can adjust the size to satisfy our needs. Right down here, basically, you see how it's controllable in many different ways. Here is basically the workspace where we build our piping systems, consisting of all those little elements, basically, circuits and pipe pairs. This is the properties window. For each of these elements that we have here, we can click on one and see a huge number of details pertaining to it. Here we have a drop-down where we can choose between modes. Peak load and equipment modes are for simulation of piping systems, see how they're going to perform under different flow rates. The purge basically that is when we want to design the purging systems or reducing header systems. I'm in purge mode now. Now this is the layout tab. I'll explain these buttons in a moment. The fluid tab is where we kind of define the fluid. So once you've sort of built your piping system, you can say, I want like 30 GPM to go through it, or 60, whatever it's going to be for your design, and then it can tell you, what your Reynolds numbers, flow rates, velocities, pressure drops are. And then we have our purging flow right here that we can manually define, or we can do it all automatically. We're going to be doing it automatically in a couple minutes. If you do want to define your purging velocities, here's where you can do it. You can define your minimum here. The default, again, is 2 feet per second, so you can put whatever you want in there. When we're actually, after we've purge optimized our systems and trying to simulate the performance, we can change the solutions. If we're using a freeze-protected solution, we choose the fluid, basically, and then it loads up the viscosities, etc., or the simulation. The automation tab, I'm going to skip most of it because it's not too important for what we're doing today, except for this pipe sizes button here. Now, GLD has a lot of pipes built into it for it to choose from when it's doing its headering design and choosing the optimal diameter of the pipes for headering, reducing headers, etc. Here are the pipe sizes available, down from a minimum of 3/8 of an inch up to 20 inches. If you're going to be basically designing a system and you know there's not going to be a 2.5 inch pipe in it, because we don't have that very often here in the U.S., you deselect this, and then basically the program won't use that pipe diameter for its sizing selection. And basically, there's a couple other things in here, but I'm not going to worry about them because it's not really germane to the headering design as part of this process. So here's how you actually use the tool. If you want to manually build a piping system, you can. And the way it works is you bring your mouse over here, and you right-click the mouse. And you could say, I want to add a new pipe pair. For example, this could be my supply return runout. Click it. Suddenly I see a pipe pair. And when I click on this pipe pair, the properties window opens up. We can see fittings for the return side, which there's nothing there because we haven't added them. Supply side fittings, flow rate information, currently 0 because we haven't done anything. General information like the name, like I could name this whatever I want, supply return. And then it'll rename it up here. You can define the supply pipe length, the diameter of the pipe type. We can do the same for the return pipe. And this way we can have like a return pipe that's not the same length as the supply pipe, for example, which is pretty common for these designs. Pressure drop, currently 0 because we haven't calculated anything. Our Reynolds numbers, currently 0. Velocities and volumes. So I'm just going to make a really simple design here. I'm going to add a single borehole here. So I can right-click the mouse over here, and I can say Add New Circuit. Suddenly I have my supply return runout and a single borehole. Now I want to see some information about this design. Currently there's no descriptive information. So we can choose the information that we want to see about these components. And we do that by going to this button here, the display button. When I do this, we see this whole list of options that are available to us. I'm going to hit the multi-select button because it allows me to choose multiple things at the same time and is more convenient. So I want to see things pertaining to the pipe pair or the headers. And I want to see things pertaining to the circuits or boreholes, the supply pipe, the return pipe. And for now, I'm not going to look at anything but descriptive terms. So I'll look at the size, the type, and the length of the pipe. You see when I do that, suddenly it has some information associated with it. The supply return pipe is a 1-inch diameter STR11, 200 feet long, and this single circuit is a 1-inch STR11, 650 feet deep. Now, why is it 650? Because on the automation tab, we set the default to 650. I didn't go over that before, but I'm just kind of giving you a little link to where that comes from. So let's say that we didn't want 650 here. There's two things we could do. First, I could go here to pipe 1 and change this to whatever, 300. Then suddenly the supply pipe goes to 300. Then I could go here and do 300. And I could do that. Conversely, we have a graphical interface for doing this as well. I could right-click on the component of interest, and I go to the Pipe and Fitting Manager. And now I basically can define the length for my supply and return pipe any way I want. Maybe I want 350. When I do that, it auto-updates that way. So basically, I built a really basic piping system, super basic. And maybe what I want to do now is simulate the performance of this simple system. So what I could do then is I'll make sure I'm in the right mode, like peak load mode. I'll put a flow rate in that's appropriate for this design. Maybe it's like 4 gallons per minute, for example. and then I hit calculate. So certainly something happened, but we can't see it because we have to define what we want to see. So I go back here and I go to multi-select. I don't care about the type of pipe. I know what it is. I don't care about the length, but I do want to see my flow rates and my Reynolds numbers and my pressure drops, for example. And now you can see this information. 4 gallons per minute, because I defined it as such. The Reynolds number is about 3,900 through this circuit, and this is the total head loss of the system is 15.8 feet ahead. And that's kind of how you use the manual approach. I could add more to this if I wanted. I could add a new pipe pair, then add a new circuit. Then if I calculate again, suddenly everything's changed. Now I have 4 gallons per minute going through this system. You can see my Reynolds numbers have dropped because I only have 4 DPM going through basically 2 boreholes now. And that's kind of the manual approach for building these things in a nutshell. So I'm going to now go through the automated wizards, the recommended way of doing this, and then show you how to do headering design really quickly. So here's how it works. Again, I right-click the mouse anywhere I want inside this white space, and I ignore the top section here because these are the manual controls, and I click Add New GHX Module. And this little wizard screen pops up, allows me to name the module. I'm just going to call it module number 1. I can tell it if I want it to be a direct return or a reverse return system. I'm going to go with reverse return. Number of circuits or number of boreholes. So I'll say I'll have 10 boreholes. The circuit separation or center to center distance between the boreholes, I'll say it's 20 feet. If I want to account for basically fittings, etc., I can put some extra length in here to save some time. I'm just going to skip it for now. Only circuit length is basically, for this case, the borehole depth. Let's pretend it's a 350 borehole. I can choose my circuit pipe size, SDR11, and I'd probably go for a 1-inch here. For my header pipe size, we could choose 2-inch, 2-inch or 3-inch. I'm going to go with 3-inch. And then I won't worry about this. This is basically if you have W bends in the boreholes. Then my supply return runout information, one-way length. Currently it's set to 200. This is the length from like your building or your manifold or your vault out to the first borehole. Let's say it's 150 feet. And let's say this pipe size is going to be 3 inches as well. So I've sort of defined the primary characteristics of this GHX module. Then I hit OK, and it builds it for me really quickly. Very convenient. I see my supply return runout, 3-inch supply return runout. I'm going to bring back the length in here. It's 150 feet long. My first borehole, which is a 1-inch, 300 feet deep. My first header section, 3-inch, 20 feet long, et cetera, et cetera, et cetera, all the way down to the last borehole or circuit. Now we've built basically the bones. I call this the bones of the piping system. Now we want to optimize it for purging. So we switch to purge mode. This is really the heart of this presentation. We go to purge mode here. When I do that, in purge mode, I know it looks a little small on your screen, but there's a little button that pops up. It looks like a straw or a pipe with water bubbles in it. I can click this, and I can choose auto adjust my purging flow rate. Then I can also choose auto size headers. And these are basically the things, the 2 buttons we activate to do the purging and headering design for us. If I go to the fluid tab, I can also activate these same controls from here, as you can see. I'm going to I'm just going to turn the first one on for the time being, auto flow. We'll set our purge velocity at 2 feet per second. Now, when we're purging a system, there's certain information that we care about, as I mentioned earlier in this presentation. So we go to multi-select. I don't care about the length of pipe. I know what the length of pipe is. I'm not interested in the Reynolds number for purging necessarily. I am interested in my flow rates and my velocities, which is what I'm most interested in, and my total pressure drop. So these are the variables I'm interested in looking at. Now what we're looking at here is the basic layout of the piping system. We have another way of looking at this, which is called, I think we call it review mode, where everything's just sort of stacked vertically. My supply return runout, my first borehole, my first header, et cetera, et cetera. Here are the diameters of my pipes. You see the header sections are all 3-inch all the way down. All my boreholes are 1-inch. My velocities are currently 0 because we haven't done anything, and my pressure drop is 0 because we haven't done anything. So if I just choose this first purge option, auto adjust purging flow rate, I'm going to hit calculate now. See what happens. What the program has done very quickly is it's looked at my design and it's figured out basically what flow rate, whoops, I forgot to add the flow rate in here. Let me bring the flow rate back in here. Basically saying what flow rate do I need to achieve 2 feet per second velocities. Just a moment, please. Let me check some here. Oh, I didn't hit the auto flow. I deactivated it. Pardon me. Let me turn this on. Because I had this deactivated, this 90 GPM, which was like a manual entry, was the 90 GPM going through here. So basically, I didn't do anything automatic. I made a bit of a mistake. So to automate it, I choose auto adjust purging flow rate. Now when I hit auto flow, it's going to look through here and figure out what flow rate I need, 57 gallons per minute, and 18 feet ahead, to achieve my target purge velocity of 2 feet per second through my circuits, only my circuits. Circuit 1, you see 2 feet per second. Circuit 2, 2 feet per second. Circuit 3, 2 feet per second. Circuit 4, Circuit 5, etc. You can see all the circuits are basically covered. I can also choose here just to look at the circuits. Now we're just looking at our boreholes, and we see everything's 2 feet per second. If I look at the pipe pairs, though, alone, if I look at the pipe pairs now, you'll see I'm not achieving 2 feet per second. So you may be thinking, what's wrong with the software? You said it was going to do this for me automatically. But you'll notice that all the pipe sizes are still 3-inch. That's because we haven't activated the program to auto-change your headering pipe sizes. And I did this intentionally. We've broken the design process up into 2 steps, basically purge optimizing the circuits, then purge optimizing the headers, essentially as an educational tool. So when we teach classes about headering, we can kind of explain why we use reducing headers. And if you have this software or purchased it, you can use this as well to sort of teach your clients and your colleagues the same thing. So now if I activate the second option, auto-size my headers, now you've kind of taken the kid gloves off. When I hit this button now, all these pipes are going to change. Okay, there. Let's take a look at what it did. First, let's look at the velocities. Now you see I'm achieving 2 feet per second velocity throughout the whole piping system, as I defined it for this, my minimum velocity. I also see my headering pipe sizes have changed. Well, they start at 3 inches, then they decrease to 2.5, then to 2, then to 1.5, then 1.25 to 1. And on the return side, it's sort of the reverse. Now, some of you are probably looking at this thinking, that's kind of cool, but we don't use 2.5-inch pipes. So to get rid of the 2.5-inch pipes, we go to the Automation tab. We choose the pipe sizes that we don't want to use, so I'll get rid of 2.5. Then we go back and hit auto-size again, and it redoes the design, but now, basically, the 2.5-inch pipes are gone. And we still have our 2 feet per second velocities. And what I'm going to do now is I'm going to bring back the circuit so I can look at the boreholes as well. So I'm looking at the full design now, and I can see it's basically 2 feet per second throughout the whole system. And my purge pump for this would figured out I need about a 58 gallon per minute purge pump with about 20 feet ahead. And this would be basically the way to design the system for purging and the size of the purging equipment you need to purge it. And that, in a nutshell, is the process of using the CFD module to purge optimize the design. I'm going to show you one other thing right now related to purging. I'm going to basically repeat the process, except I'm going to do it a lot faster to show you how quickly I can do it. And I'm going to use a 2-inch supply return runout rather than a 3-inch to show you the difference. So I'm going to build a new GHX module down below. We're going to have 10 circuits because we have 10 in the first one. We had separation of what? I think it was 20 feet. What was our depth? It was 300 feet deep. Our circuit size is a 1-inch. Our one-way length is 150. And, oh yeah, my header size is going to be 2-inch now. Instead of starting with a 3-inch header, now I'm going to start with a 2-inch header for, and then for my supply return runouts too as well. Now basically I have a second GHX module here with my supply return runout 2-inch, 2-inch, 2-inch down to my last circuits, and then I have my 3-inch here. Now let's remember that with my purge optimized 3-inch system uses about 58 gallons per minute and about 20 feet ahead, 58 and 20. So I'm going to delete this now. We're just going to look at the 2-inch case. I'm going to purge optimize it really quick. I'm in purge mode. These are both active. I hit auto size. Okay, I'm done. I just purge optimized the 2-inch. Let's look at it. goes from 2-inch, drops to 1.5 inch, so the header size is dropped down there. What you'll notice now I need about 59 GPM, which is similar to the last one, except my head loss now is over double, 46 feet ahead. So using the CFD module, you can very quickly compare and contrast your GHX module design. Say, what if I use a 3-inch pipe here? What if I use a 2-inch? And then it takes a few seconds to optimize it and see what the results are. It's very powerful for doing what-if modeling, or you're basically piping up or designing your piping system. So this is the end of the basic presentation. I'm now going to open this up to any sort of questions. If anyone has a question, I'd prefer it if you raise your hand. By the participant list, there's a little button that says raise your hand, and if you push that button, then I can basically see that you have a question. I already see I have a question. Okay, so Connor, can you hear me? Can you answer your question? Ask the question?
Yes, can you hear me?
Yeah, loud and clear.
This was really great. Can we have the same type of run-through manifolds, or some of the more complicated things that occur beyond the, we're kind of going over one supply and one reverse return header, maybe one vault, or maybe one heat pump back at the building. But as things go on and projects get larger, there's more vaults and more heat pumps and so on. Can you go over some of that, or is that a different class?
We're planning on having a series of these classes. We're going to save the details for a future class, but I can very briefly sort of introduce the idea. Connor's basic question is, how do you do more advanced things? As a reminder, the GHX module here is sort of the fundamental element of your system. You want to basically build these, purge, optimize them, and then we can basically build them into larger systems. We can right-click, and we have these things like manifold wizards where we can build manifolds or vaults, and then basically build those systems. And then once you've built the manifolds, you can basically take these things, copy and paste, drag and drop, do different kinds of things, and build very, very large systems very quickly. But that's sort of outside the scope of this presentation today. We'll certainly be addressing that in future presentations. Thanks, Connor. So, Connor, can you take your hand down now that you've just hit the raise hand button again to lower it? Anyone else have any questions about anything? Just give people a few seconds to think. Also, if you have a question, you can also, I received a chat message. Let's see. Lucas, please unmute your microphone and feel free to ask. Okay, I can hear you. Great.
You said your module based off of that velocity that you want for your purging, but ideally you'd want to size your whole circuit based on what your regular flow is going to be, not based on your purging rate. Correct?
Yeah, it's interesting. Most of the reducing header issues, we go from like 3 inch to 2.5 to 1.5. That's basically for the purging optimization. When we're actually running these systems on a day-to-day basis, we're not going to be using these flow rates. It's going to be a much lower flow rate. And your question, so basically when you design your heat exchanger, let's say you have a 100 borehole system, say it's a 10 by 10 grid, and the boreholes are 300 feet deep. You choose like whatever 1 inch diameter pipe. You're going to have a flow rate going through those that's maybe going to be way lower than your purging flow rate, so that your pressure drops are much lower. We've just talked about the purging side of things here. The operational would be a very well, if we wanted to do that, we'd switch to operational mode, like peak load mode, and then we'd run it with a different flow rate here, like maybe 30, and then you see what happens to your, for example, I'm not saying this is the right one for this design, but you see how your velocities are now like about 1 foot per second here, as opposed to what they were before.
Yeah.
Yeah, but you're right.
Mainly, I just wanted to say, because that's how I do all mine, is you got to decide it. For people maybe that are newer to this, I wanted to say that so they don't size their loop field based off of purging. They want to size it based off of what their flow of their actual system's going to be.
Yes, very, very important point. I'm just going to reiterate that. Lucas pointed out that you know, these flow rates and these velocities that we're looking for purging are very high, very fast, and have a lot of pressure drop or head loss. When you're actually running your system on the day-to-day basis with your circulation pump, you're going to have much slower velocities, much lower pressure drops, because we don't basically, because all we want for day-to-day operation are Reynolds numbers that are maybe in the max 3,500 range. We don't need velocities or anything like this for regular operation. Thanks, Lucas.
Yep.
So any other questions? Anyone have any questions? So, okay, so,
Looks like Connor has another question.
Connor, do you have another question?
Sure. Nobody's else is gonna ask. I wanted to kind of go in. I'm not sure if it's a workaround, but as you just explained, you would size your pipes according to the purge requirements. And then what you can do after all your pipes have been automatically sized, your headers and your circuits, you can go back to just normal peak load operation and run it at the, you know, not that high velocity, but at the lower velocity, the actual realistic day by day flow in those size pipes. In terms of, my question is I can lower the gallons per minute and keep kind of getting different results, different Reynolds numbers out of the program and so on. So if I was going to look at a system that had variable speeds, it would take a lot of time, but I could kind of make some engineering assumptions by placing different gallons per minute, different flow rates into that existing size system. Do you have anything to say about variable speeds?
Ben, can I take that one?
Yeah, go ahead.
The trick is when you're 100% right, because the downsizing and checking down of your fluid flow in the system and its operation, its realm numbers, one of the things that people overlook, the value of this module is the determination if you're actually achieving that turbulent flow state or not, or if it's even worth going after the turbulent flow state. Sometimes you might notice that the flow rate itself is so far away from turbulent flow that you might be better off just designing around the laminar flow. So it's something that the module will help you take into consideration. And then on top of that, you actually, you know, further on your question in terms of the VFD, depending on how you design your loop field and what you're designing it to achieve, as long as you design a system that at peak operations and you achieve the maximum flow rate you need. If you design a system to turbulent flow and you design a VFD system that can achieve the flow rate necessary, if you're only operating half the heat pumps, you don't necessarily need to operate at that peak, and thus that knockdown flow rate won't really necessarily negatively affect your heat transfer or the overall design, because you're not pushing the loop field to the load that you've designed it for. You might only be using half, so achieving that maximum flow rate may not be necessary.
Great. So I also had a question that was texted in or chatted in from Will, talking about branch pressure terminology. So basically, let's look through the pressure drops here. I'm going to get rid of some of the excess stuff to make it a little cleaner here. Get rid of the Reynolds numbers here. Emission, velocity, we'll just make it simple. So basically, we have, like for example, what I'm doing now, I'm showing pressure drop and total branch pressure drop. Let's look at the supply return runout, the highest level element. You see we have 4.2 feet ahead here, 4.2 feet ahead, 4.2 feet ahead, and 16 feet ahead. The 4.2 feet ahead here is the supply side pipe on the supply return runout. The 4.2 feet ahead is basically the head on the return side on the supply return runout. And the 16.2 feet ahead is basically the total head loss of this element and everything below it. So the total head loss of this GHX module under whatever flow rate we're under 30 GPM with with water. Let's just go with water. Now, when I've done it with water, underwater at 30 GPM, our total head loss of this module is 13.9 feet ahead, which is a very reasonable head loss for a GHX module. If we look at this circuit, for example, we have 2.5 feet ahead on the supply, 2.5 on the return, and then about 5 feet of head loss total for this circuit. And then we just kind of go down that way and that way. On this GHX header section, we have 0.4 feet ahead on the supply, 0.2 feet on the return. Ignore the fact that this is 0. It's something to do with the math, very complicated. But that's the head loss in this particular element here. You can, if you went through and added all these head losses up, plus this and this, it would come out to 13.9 feet ahead for a single flow path from basically start to finish. Okay, so I have another question that came in over chat. Let me check this out. Okay, so actually that wasn't a question. Any other questions anybody has? Any questions about anything related to this? I do know that I think most of the people in this class already have GLD, and we're happy to have you as customers. For those of you that do not or don't have the latest and greatest versions, for really the first time in a long time, because of Earth Week, we decided to offer a 10% discount this week only. So that offer's on the table for the end of business today. Any other questions about anything related to the CFD module?
Thank you very much, Dan. I appreciate you putting this presentation on. It's been very, very informative.
Okay, wait, someone asked me one more question, Dave. Mark asked me, where is the reverse return pipe length calculated? Okay, so basically, this program, it doesn't calculate the length. It helps you with the sizes. You define the length. So, for example, the supply return runout length that I defined, there's two ways to look at it. I could look here and see the supply length 150 feet, the return type's 150 feet. Or I could go like this, basically, and choose to look at the lengths here, and then they're right there. So if you were doing something that was like a horseshoe design, where the return length is much shorter than the supply length, maybe I'd put 30 in here. So now my return length's 30 and my supply length's 150, and that's how you model like a horseshoe design. But the program doesn't tell you, you tell the program the lengths for your design, and the program helps figure out the diameters of the headers. The program's not going to be changing the diameters of your primary circuits. That's your responsibility to choose whether it's going to be a 3/4 inch, 1 inch, 1 1/4, 1/2, whatever. Any other questions about anything? You turn your webcams on and put your palm in front of it. I can read your palm too if you like. Bad joke. Okay, so it doesn't look like there are any other questions. If you do have any questions that pop up in your head after this presentation, feel free to email us, like Jeff, for example. We will get back to you. And again, thanks for your time today. Thanks for thinking about GLD. Thanks for designing geothermal systems. I wish there were a lot more in the ground than there are today.
Yeah. And that pretty much wraps up the presentation. So, as Dan said, if everyone has any questions, please, or any further questions, please feel free to email them in. Other than that, hope everyone has a good weekend. Thank you.
Thanks.